Now we're going to get into some serious applications of the conservation of momentum. None of those silly applications for us. This learning target asks us to consider collisions, different types of collisions. So we have elastic and inelastic are two types, and then the third type is a special case of inelastic. We call it completely inelastic collisions. So first off, I found some resources that I thought were useful. Hyperphysics is a great page that has lots of good information for physics knowledge. So I found their definitions for elastic and inelastic collisions, and I thought would be useful here. In an elastic collision, whatever kinetic energy we started with is going to stay as kinetic energy. So the kinetic energy before the collision, total for all the objects involved in the collision, is equal to the total kinetic energy after the collision. Now, in an inelastic collision, some of that energy is changed into another form. So often we would, always really in the real world, we're going to be creating some thermal energy. We cause these molecules to vibrate a little bit when we collide. Other energy types will be involved as well. Now, really, there are no perfectly elastic collisions, but some of them are close enough that that's a good assumption for us to make, and we can make some good predictions with that. And then the perfectly inelastic collision is one where as much kinetic energy as possible has been turned into other types of energy. Typically when we see a perfectly inelastic collision, what we'll end up with is two objects that stick together. So About.com had a nice description of this and talked about football players tackling one another. So after they make contact initially, and it's shown in this picture here, those two players are going to move together as though they were one large object. But in any of these cases, momentum is going to be conserved. So total momentum at the very beginning of the problem is equal to total momentum at the end. For a perfectly elastic case, we also know that the total kinetic energy at the beginning is going to be equal to the total kinetic energy at the end. Now, of course, energy overall is conserved in any case. What makes elastic collision special is its kinetic energy conserved. So let's try a couple of problems with this. First off, we'll have a collision between two steel balls, and I chose steel because it doesn't deform much under contact. Things that stretch out or compress a lot, they tend to have a lot of energy lost in these collisions, or not lost, but changed from kinetic to another form. So in this one, we can work these problems with very little starting information because we have two equations that we can rely on, which means we can have two unknown values. So in this one, we know the two masses and we know the starting velocities for each, but we don't know the ending velocity for either. So there's two unknowns and two equations we need to, two equations that we can use. So you might get the idea that this is going to be a conservation of, this is going to be a system of equations type problem, and you're right. So let's write out the equations that we have. First off, conservation of momentum. The total momentum initially is equal to the total momentum in the final state. And so here we've got two objects. So we've got the mass, we'll call it mass 1 naught, velocity 1 naught, plus mass 2 naught, velocity 2 naught is equal to mass 1 times velocity 1 final, plus mass 2 times velocity 2 final. Now mass 1, I'll call that 2 kilograms, and the initial velocity there is 2.5 meters per second, plus mass 2 was initially at rest, is equal to 2 kilograms times velocity 1 final, plus 4 kilograms times velocity 2 final. So this one simplifies down to 5 kilogram meters per second is equal to 2 kilograms times V1 plus 4 kilograms times v2. So not enough information to solve just with conservation of momentum. So now we're going to go to conservation of kinetic energy, because this is an elastic collision. So we say the total kinetic energy initial is equal to the total kinetic energy final. So kinetic energy is 1/2 mv squared, so this will be 1/2 m1 v1 naught squared plus 1/2 m2 v2 naught squared is equal to 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. And now we can plug in. We've got 1/2 times 2 kilograms times 2.5 meters per second squared plus initial velocity for 2 is 0, so this whole term will be 0, is equal to 1/2 times 2 kilograms times v1 squared, v1 final, plus 1/2 times 4 kilograms times v2 final squared. Or this simplifies down to, oops, that's not right, 6.25 kilogram meter per second, meters squared per second squared is equal to 1 kilogram times v1 squared plus 2 kilograms times v2 squared. So now we have two equations, each with v1 and v2, and so we can solve these two equations, this one here and this one, as a system of equations now. Now at this point it's really no more new physics, just the math behind this. So you may want to skip ahead if you're feeling comfortable with the math on this part. To solve a system of equations, we have a number of different routes that we can take. Graphing is always a nice way to approach these problems, especially in ones like this where we have the squared in there, and those tend to be kind of a pain to solve. But certainly another method would be to solve by substitution. So let's do that. I'm going to make an equation that has v1 equals, and then I'm going to substitute that into the other equation. So v1 in this first equation is going to be equal to, I'm going to drop my units for simplicity's sake, 5 minus 4v2, and that's all over 2, is equal to v1. I'm going to do the same thing down here. 6.25 is equal to, 1 times v1 squared plus 2 v2 squared. And then I'll substitute this in down here. So I get 6.25 is equal to 2.5 minus 2v2 squared plus 2v2 squared. So now 6.25 is equal to, let's see, 2.5 squared, so that'd be 6.25. And then do my outsides and insides, so that'd be a negative 10 v2. And then my last times the last, so that'll be 4 v2 squared plus 2 v2 squared. So now this one goes to, it subtracts 6.25 from both sides, so 0 is equal to negative 10 v2 plus 6 v2 squared. And so my possible solutions to this would be when v2 is 0, or when negative 10 plus 6 v2 is equal to 0, which would mean that v2 is 0, or let's see, 10/6 or 5/3, or about 1.6 1.67 meters per second squared. And then I'm going to take that and plug it back into this equation up here. So V1 is equal to 5 minus 4V2 over 2. So V1 then could be, if we chose a value of 0, then this term drops out and we get 2.5 meters per second. I'll just put a note down that those two go together. There we go. Or that V1 could be equal to 5 minus 4 times 1.667. So 5 minus 4 times 1.667, and then divided by 2. This will give us a negative 0.834 meters per second. And again, I'm going to put a note that those two go together. Okay, so now we have two possible choices for our final velocities. How do we figure out which one it is? Well, in this situation we had our little ball initially moving to the right, our 2 kilogram one. We call that mass 1. And this one was mass 2. In this collision, if we look at this first case where we had V2 is 0 and V1 is 2.5 meters per second, that's exactly what we had in this initial case. So mass 1 was moving to the right, mass 2 is still. But in the final case, that can't be the one that happened because these two collided. If this one is still moving to the right after they've collided, then it would have had to pass right through mass 2. And we know that that can't happen, so we can eliminate this as an answer. And we know that our final answer is that V2 is going to be 1.67 meters per second squared. Meters per second, not meters per second squared. And V1 is going to be negative 0.834 meters per second. So this one is going to be moving over this way at 1.67. And this one's going to be coming back the way it came at 0.834 meters per second. Okay, one more problem with the collisions. Now we'll do a completely inelastic collision. So in this one, we're going to have two cars that will collide. Remember, in a completely inelastic collision, we have our objects stick together at the end. So initially, we have, let's see, one car traveling to the north. Call this car A. And this one is going to be car B, the truck. And then B is going to the west. And this one's 23 meters per second, and this one is 18 meters per second. And then in our final state, we have this big mass of A plus B. They become entangled, and they're moving at some velocity unknown. We're trying to solve for that unknown velocity. So here we can't use conservation of energy. It's not an elastic collision, but we can use conservation of momentum. So we can say that the momentum for object A plus the momentum for object B has to be equal to the momentum for this A plus B conglomerate. Now, momentum is a vector quantity, and we see here that we have vectors at two different directions, so it's going to make sense to treat these as two separate problems. One for the momentum in the x direction, initial, and let me give myself a little space to total momentum in the x direction initial equals total momentum in the x direction final, and total momentum in the y direction initial equals total momentum in the y direction final. So initially in the x direction we have A moving straight to the north, no contribution to the x direction momentum there, and then B is traveling to the west. That's in x direction, we'll call that negative. So B has a mass of 2,400 kilograms and is traveling at a speed of 18 meters per second west, so I'll call that negative 18 meters per second. And that has to equal the total momentum at the end, which is going to be one large object with a mass of 1,200 plus 2,400, so that'd be 3,600 kilograms times its velocity in the x direction. So now we can multiply the 2,400 by the negative 18 and divide both sides by 3,600, and we get negative 12 meters per second is our velocity in the x direction. And then in the y direction, we start out with car A moving upward or moving to the north, so we'll have the mass of that car, 1,200 kilograms, times the velocity in the y direction, 23 meters per second. And then the truck, initially just moving to the west, so no contribution to the y part of momentum. That's going to equal the total mass, 3,600 kilograms, times the y velocity final. So now we can do our 1,200 times 23, and then divide that by 3,600, and we get 7.67 meters per second for velocity in the y. Now we have the components of a vector. We just need to put these together to get our overall velocity vector. So we have 7.67 meters per second going to the north, and let me draw that a little better to scale. 12 meters per second going to the west. And so now we need to find our resultant vector going from here to here. And that is going to be our overall velocity, and we'll want to get this angle. So the magnitude of that velocity is going to be equal to 12 meters per second squared. So I square that magnitude, plus 7.67 meters per second squared. So the velocity then is going to be 144 plus 7.67 squared, and then square root that, and we get 14.2 meters per second. And then the theta, the angle there, is going to be the inverse tangent of 12 meters per second over 7.67 meters per second. So inverse tangent, there we go, of 12 over 7.67 is equal to 57.4 degrees. So the final velocity then for this car-truck combination right after they collide is 14.2 meters per second at an angle of 57.4 degrees, and that's measured from north rotating to the west, so west of north. And that is all for our collisions.